Hi, my name is Paige Allen, and today I will be talking about Lab 4 called Oscillation. The agenda for today is I'll be talking about my introduction and purpose, some background physics concepts, my codes, potential errors, and then some concept questions and answers. So the purpose of the lab was to determine the motion of a mass oscillating vertically on a spring and compare that to the ideal parameters. The spring was swinging on an arc while oscillating up and down on the spring. So on the top you can see there's an actual photo of the spring mass system that was connected to a fixed focal point. And on the bottom photo, you'll see that that was an actual program that we used called Tracker to be able to do this lab. And each part was recording the given movement of the spring. I know it doesn't show it on there for some reason, but the system was the mass and the spring. The environment was the earth, so gravity, air, and the fixed point support that the spring was connected to. And like I said, we used Tracker, but then we also used GlowScript to be able to write the computational model. The two main principles that we use is the Newton's second law of motion, basically the kinematic equation, so the velocity final or the velocity update formula and the position update formulas. This was used throughout to be able to track the movement of the mass on the spring and be able to make the code run more smoothly. And then the energy conservation principle was also used, which is on the left-hand side, which basically states that the summation of the energies of the system should remain at the same fixed number throughout. So the change in the potential energy, which is the gravitational potential energy, plus the change of the kinetic energy, plus the change of the spring potential energy, should all equal the same change in energy throughout. But whether or not one of those is positive or negative will depend on where the system is going throughout that entire observation period. And then we have the kinetic energy equation, potential gravitational energy equation, and the spring potential energy equation. So our initials, the mass of this mass that was on the spring was given to us at 0.402 kilograms, and then the length of the spring at its fixed support was actually considered to be 0.7 meters. You'll see on the top right hand, again, the photo is not showing, it's showing a white screen, but actually the actual video would be right there, and you can see all those red dots throughout the video picture, and that's actually just us tracking each of the center points throughout. And that gave us our information on the right-hand side of that photo. With that information, we calculated the average periods of the x and the y direction, and then we averaged that to be able to find the overall average oscillation period. And that was used to be able to find the spring constant stiffness, which was 6.735, and then we used the spring equation to be able to determine what the original length of the spring was, which is 0.115. This was then used for our code to be able to give the ideal expected outcome. So on the left-hand side, those are all our basic initials that we're given. The ball position, G, the spring stiffness, which was 6.735, you can see right there, and then L naught at that 0.115. And then on the right-hand side was all of the changing parameters throughout the spring mass system's movement. So you'll see that we have the force of the spring equation, and the F net total was that spring and the gravity, which was causing the kinetic motion. Then we have the velocity update formula and the position update formulas, and the energy conservation principle at the very end of the statements to be able to determine how energy changes throughout. So this was our results. On the left-hand side, you'll see the change in the energy, and pretty much that overall energy, highlighted in yellow, remains close to that zero line. And we see the spring energy in green, gravitational potential energy in red, and kinetic energy in blue changing throughout, but overall the summation of all of them is equal to zero. On the right-hand side, you'll see the position updates, and compared to the model, the experiment was a lot more wobbly. It didn't reach quite that height and that distance that it could have, especially for the Y position, not significantly. And there's a few reasons for this, actually. So there could have been some calibration issues with the tracker. Air resistance could have played a big factor into this, as well as the rotational energy that the spring on that fixed point actually creates as it's moving and oscillating at the same time. And then, of course, GlowScript could have had some reading errors, as even if the code is working, there could be some bug issues regardless that confuses GlowScript. Some concept question answers. The first one was, is the energy principle satisfied through this modeling? And you'll notice that it was very close to doing that, but there are some slight deviations. So on that delta E yellow line, it's right by zero, but you can see it tapering up and down just slightly. And that could be due to some energy being lost through air resistance, and then that rotational kinetic energy that's not considered when it's turning, because it was creating a movement that was oscillating but also swinging. For the calculating oscillation period of both x and y direction, comparing it to each other, you'll notice that the period is actually the time for the total number of oscillations you choose divided by that number of oscillations. So I chose 5 for this one instead of 3 like the actual computational model, and I got an average between 0.9954 for the x and 0.910, and that's a difference of about 0.07, making the x a lot greater. Again, that could be likely due to the drag force or some errors entering into it. The way the spring was also moving could also have hindered it drastically. But that same thing is reflected in the in the photograph in the middle right there. As you can see, the actual X point that it reaches on the top is different for the Y position. It's not the same oscillation, which was what we found.